He's actively involved in various research topics in the field of UV, thermal energy storage, and other engineering aspects. We also have Mr. Ekansh Kshetrapal, who is the Senior Manager Applications and Business Development at Encapsulated Technologies. And he also also has a background of more than 13 years in the HVAC industry, focused on design and selling of various products and specializing in thermal energy storage systems. He has hands-on experience of installation, commissioning, troubleshooting of these systems, and also R&D on these systems. And he has got training in design, production, and operation of thermal storage systems. So I hope that the knowledge of these two gentlemen will benefit all the attendees, and we will be able to implement these systems in our projects, as they're very important for our country as well, as the cooling needs increase and we move towards a decarbonized world. So I will hand it over to these two gentlemen to start the training. Thank you.
Thank you so much, Mr. Suhas, for the wonderful introduction. Hello, everyone. My name is Ekansh. Like he has already introduced me. So I will be discussing about thermal energy storage, cool thermal energy storage as a whole. And we will be understanding different types of thermal energy storage. I'll just take you through the. Is my screen shared? Can everybody see? I hope. So cool thermal energy storage system, and the topics that we will be covering will be we'll understand what is cool thermal energy storage. We will also try to understand the unit of thermal energy. We will also try to see how thermal energy storage has great potential for saving electrical demand, and how thermal energy storage does it. We will also try to see what all applications thermal energy storage can cater to. And then we will try to understand in detail two specific types of thermal energy storage, that is stratified chill water thermal storage, and then we will also understand ice-based thermal energy storage. So what is cool thermal energy storage? In cool thermal energy storage, we have a storage medium in which we try to store the cooled energy with the help of a chiller when there is a low demand, and try to use it when there is a high demand with lesser installed or operating chiller capacities. What is the unit of thermal energy storage? So the unit of thermal energy is ton hours. Tons is 1 ton is 12,000 BTU per hour. So that is essentially a power. When we convert that to energy, it becomes ton hours. So when we multiply tons by hours, it becomes BTU, and which can also be converted into kilowatt hours. So that's energy. So chiller capacity is specified as tons, and thermal energy storage capacity is specified in terms of ton hours. Potential of electrical demand saving. Let us have a look at these graphs one by one. Let us see the first one, the one on the left side. Like this graph typically shows a load profile of the building, and it's a 24-hour load profile, and you see that there is a load. It is starting from here and goes until here, and if we try and calculate the average load of this building, so the peak load happens to be 1500 kilowatt at some time. However, the average load over 24 hours happens to be nearly 800 kilowatts. These figures are just to take an example. However, what is to be seen here is that despite the average load being 800 kilowatt, one has to install a 1500 kilowatt chiller plant. So the load factor here, which is the average load versus peak load, is actually very poor. Thermal energy storage gives us the option to have a lesser installed connected load and have our machines store the thermal energy in the hours when the load is less. Let's say in the night hours. In these hours and in these hours, if the connected load is nearly 900 kilowatt, because our load remains the same, the building load profile remains the same. So with 800 kilowatt average load and 900 kilowatt as a connected load, the machines which we use for charging the thermal storage at night. So this gives us a far better load factor, that is 88% average load versus peak load, and we are still able to cater to the entire load. So the idea here is to see that how we can cut down on our connected load. That is how we save on demand. We could also see this from the perspective of uh, around the year. I mean, these are 12 months. These are 12 months, and it's generally during the hot summer months when the load is peak. In the other months, the load is not that much. But we still tend to install chillers of a very high capacity, of the peak capacity in general. This is also possible to actually cut the demand, that we can have chillers installed of lesser capacity and use thermal energy storage, like just we did in the other case, in the hourly load uh, pattern. This is for a daily consumption profile, and this is the seasonal electrical power demand load. As we all know that HVAC uses nearly one third or even more of the total building electricity. Now, this is to understand that how, with the same power plant, how, see, there is a power plant, there is electricity being taken from the grid, and see, with thermal energy storage, what is possible is that this scenario is without thermal energy storage. Like there was a power plant that was catering to four buildings, 1 megawatt each. So 4 megawatt it was catering, and let us take the average days of operation to be 250, and let's say it 8 hours a day, that we consider. So 8,000 megawatt hour is what can be availed out of such a plant within the four buildings. However, if there was a provision for thermal energy storage, let's say in all these buildings, then it was possible to reduce the connected load, let's say down to zero point 0.8 megawatt, and same power plant could produce 25% more sellable kilowatt hours, as well as the connected load could be connected. I mean, the electrical load could be connected to five buildings instead of four. So you see, the sellable megawatt hour has now increased with the same amount of power plant. So in a way, we are also reducing the requirement to produce more power plants. Plus, another advantage that thermal energy storage has is during power cuts, for buildings and campuses where the power cuts are frequent, even for an hour or two, running large chillers on DG could be a very, very expensive affair. So if even a backup of those 2 3 hours when the power cut occurs could be planned with the help of thermal energy storage, it could also be a great proposition for saving on diesel cost, on the diesel generator cost. Plus, plus when you are able to reduce your chiller capacity, you are also cutting down on your uh, diesel DG requirement. So what TES does, thermal energy storage system downsizes the chiller capacity of the chiller plant because of sharing the load during the day, and which further results in the lesser backup generation capacity required, like I just mentioned, and then it results in smaller diesel generators and lesser diesel consumption also. So we will now try to understand different types of thermal energy storage. Uh, so it can be broadly classified into two categories. One is chill water based, another one is ice based. And chill water storage can be further classified as stratified thermal energy storage, and it can also be classified. And then the second category is a buffer tank. Also, they are also used to store chill water. And we will also understand further classification that stratified TS tanks are available with radial disc diffusers, and they are also available with octagonal diffusers as well. Then we will go into the detail, and then the ice thermal storage, we will try and understand different technologies, uh, like ice on coil and encapsulated ice, and to further classify them. So internal melt, external melt, and we will also understand spray type systems and nodules submerged in monoethylene glycol. So chill water thermal storage tank. So this is the first category that we are trying to understand here is stratified thermal storage tank, in which the working principle is that it works on the thermal stratification because of the density difference. Like in the same tank uh, that is vertical, like I've written here, it's a vertical tank in which when the chill water is discharged and the return water is coming back from the top, the idea is that mixing should be controlled. No mixing, no turbulent mixing should happen between the two. And for that, the densities of supply and return water are different due to the different temperatures. So, it's the density difference that causes the thermal stratification to happen naturally. Top and bottom diffusers are provided to maintain laminar flow to avoid turbulence. So, this is what a stratified thermal storage tank comprises of. The diffusers are the heart of the system, and they are the ones that ensure that the mixing that the water is released inside the tank in a manner that the mixing does not happen, because turbulence should not happen. Even only if we can ensure that the flow happening inside the tank is laminar, and and rest will be taken care because of the density difference. So stratification will happen. This curve here shows that water is heaviest at 4 degrees centigrade. So 4 degrees centigrade, the density of the water is maximum. And you see at an increased temperature here at 14 degrees centigrade, the the density is somewhat low. So it's the density difference that separates them. Now, stratified tanks are also available with octagonal diffusers. See, in octagonal diffusers, there is a web of pipe, as you can see here in the picture. It has high velocity nozzles, and it's lightweight in construction, and it is generally viable for large tanks, very huge non-pressurized fan tanks. That also we will understand what they are. Uh, and their MOC, the material of construction, I don't know if I mentioned here, but these are also in SS304 and polycarbonate, although we will talk about diffusers separately. Okay, we will talk about them ahead. Uh, SS304 and PVC pipes is what these diffusers are made of. And then we have stratified thermal storage tanks with radial disc diffusers. Yes, you see in this picture here, these are plate type diffusers in radial in construction. They are sturdy in construction because they are of SS, and either only SS or along with the combination of SS and polycarbonate boards. And the objective of these diffusers is to release the water inside with a very low velocity and very low release and suction of water, and it is suitable for high and low volume tanks for both the tanks. By both the tanks, I mean that one is where you have a long hours of discharge. I mean, as long as 8 9 hours, and they are huge non-pressurized tanks. And the other category is used for uh, the the backup the backup duration. Let's say for 5 10 minutes, where they are pressurized closed tanks. They can be termed as low volumes. We will understand them separately in the slides to come. Then there's also a category. They are called buffer tanks, and buffer tanks are they can be vertical, they can be horizontal also, and they have baffle plates inside the tanks. A horizontal one can have three baffle plates, and a vertical generally has one. The design is based on the capacity to hold the exact chill water volume for the stipulated discharge duration. For example, if we are planning for a 5 minutes backup, so we multiply the flow. I mean, the flow is multiplied by the, uh, the duration, and that's how the volume is arrived at. And this tank is exactly of that volume. So major consideration for capacity calculation are flow and the time of discharge. And in here, the mixing, the stratification that we were talking in the other tank, the stratified tank. So the mixing is not accounted for in this tank, and they can be vertical as well as horizontal. What are the applications? Some of the applications of chill water thermal energy storage. They can be a process cooling plant. It can be an industrial application. These are also used in turbine air cooling, and very promptly used in data centers these days, and district cooling plants also extensively used. And there are other special applications also for these, for which chill water storage may be used. Ice based thermal energy storage. We will now understand ice based thermal energy storage and its types. So in here, the cool thermal energy is stored in terms of ice, in the form of ice. And ice is formed, you see, by circulating the fluid with a very low freezing point. It is called monoethylene glycol solution, which is used to circulate inside the to circulate across the tank, and it forms ice inside the tank. And so special brine chillers are used to generate the desired fluid temperature. I mean, if one has to form ice, there has to be a fluid which has to go below the freezing point of the water. So that is the only something that can cause to make ice. So later, ice formed cools back. I mean, how? See, when the ice is forming, we are storing the thermal energy, and when we need to use the thermal energy storage, then then the brine solution is passed over the ice to extract the cool energy and supply it to the load. So here is the chiller, and this is the tank, and this is the cycle. This is how the cycle goes, and we will look at other schematics to get a clear understanding in the slides to come. So while understanding types of ice thermal storage, we have ice on coil technology as well. There is ice on coil technology, in which there are further two categories, and one is internal melt, and the other one is external melt. Internal melt is, see, in this case, the tubes, there are polyethylene tubes in which uh, the brine solution flows at negative temperatures, let's say at -5 degrees centigrade, and around this tube is water. Around this tube is water. So when the flow happens, when a fluid of minus 5 degrees centigrade flows across it, the ice starts to form on the outer surface. So it forms on the outer surface, but internal melt is something when the hot brine solution is made to flow across these tubes again. The melting of the ice starts from the inside here. So this is called internal melt. Very similar to this is another classification of ice on coil technology, that is external melt. The ice formation happens the same way as explained previously. However, the in the external melt, the chill water is made to pass to, uh, over these ice, over the ice formed, and that is how the cooling is extracted. So that is external melt, ice on coil technology. And then there's another category in ice thermal storage is encapsulated ice technology, where chilled water is encapsulated inside the capsules. And see, such are the capsules, although there are different models available out there, but more or less it's like this. Like the water filled inside is generally 87, 85%, something like that. And there are air pockets as well. So when the ice is made, there there happens some expansion in the volume. So the entire capsule is occupied by nearly 96% of the ice, and the remaining is air. So that is encapsulated ice technology. And the thermal energy stored thermal energy is stored in polyethylene eutectic balls, and in a no storage condition, like I explained, there is a somewhat lesser volume of water. And so yeah, it's mostly later the stored ice transfers cooling to the brine when required. So once the ice is formed, of course, the cooling can be extracted out of it by passing brine solution over them. We'll also understand more clearly what brine solution is later. Now, within the encapsulated ice technology, there is another technology which is ice spray technology, spray type technology. Now, in this technology, the brine solution travels down over a stacked ice capsules with gravity to form ice inside the capsules, or get cool energy from already formed ice. So ice capsules are here, and this brine solution is being sprayed over it. And this is not a closed circuit; it is just being sprayed, and the brine falls at down to the basin uh, to contain the cool energy down there. Now, this is also an encapsulated ice technology, in which there are nodules, and nodules are also uh, the encapsulated ice only. But in this kind of a setup, the nodules are submerged in the entire brine, in the entire tank that contains brine, a tank that is full of brine. So that's the difference. That is called nodules submerged in monoethylene glycol solution. Some of the applications of ice thermal energy storage. It is suitable for malls, retail complexes, commercial complex, process cooling, industrial application also. Sometimes for special applications like milk chilling plants as well. So we will now get on to the design part of thermal energy storage system, and two systems that we will be focusing on specifically as far as the design is concerned, because there are a lot many categories of systems. We cannot try and understand each and every design, so we will stick to two types of we'll stick to one category in each, chill water as well as ice thermal storage. So first we will talk about stratified thermal storage systems, and then we will talk about ice thermal energy storage systems. Let's say a spray type. So stratified thermal energy storage system design, uh, electrical demand. So we'll try and understand this in two ways. I mean, there can be there are two major applications, two major purposes for which stratified thermal storage can be used, is widely used rather. So one is electrical demand management, and the other one is emergency backup chill water supply. So let us try to first understand it from the perspective of demand management. We already understood what demand management is previously when we are trying to downsize our connected load. So, so what is the basic data that is required for designing thermal storage system? See, in the first place, we need hourly load data, and it should be like this: heat load. Let's say this is the heat load. This is the hourly load. These are 24 hours, and this is generally the peak load, and very often the diversified load across the entire building or a campus. Then we also need supply and return temperatures. That what is going to be the supply and return temperature across the load. Space availability is also something that should be observed if planning for chill water thermal storage tank. So we start with a load distribution profile. I mean, when we have an hourly load profile, we start with the load distribution profile and try and figure out what is the what is the optimum chiller capacity that I should design for, and what should be how much load should I keep on thermal energy storage, because it is to be seen whether do I have sufficient charging hours for charging the thermal storage. Like this is a typical load profile for one of the projects we did, and and in here there are the load is the load is 1600 tons. You see the peak load here is 1600 tons, and there was going to be a four chiller configuration, 4 into 400 tons. However, it was designed for, I mean, it was opted that thermal energy storage system will be used, and three chillers, each of 400 was used, and the balance 400 tons load was passed on to the thermal storage. So, so let's say this was nearly the thermal storage capacity, and nearly 1300 ton hours was the thermal storage capacity. I would also like to draw your attention towards this column, and this column is a tariff rate, which is also a key factor that how should we plan our discharge pattern, and in what hours should we try to avoid running chillers as far as possible, and so things like that. That what is the most optimum way of operating? What is the most optimum operating strategy to be applied? So that's how we arrive at the thermal storage capacity. You see, it's 1300 ton hours in this case. So so our design calculations will be based on this. Like the peak load is 1600 tons, and the chiller configuration is 400 tons, three working, one standby, and the peak load on thermal storage is 400, like we saw, and the purpose here is peak shifting and electrical cost saving. You see, this is the 24-hour load profile, and not the 24-hour, but from the hour of operation, from the 8th hour down to the 23rd hour, and out of which this was the connected load that was saved, and this much load was being taken care by thermal storage. In this case, with such a huge storage capacities, although there are larger storage capacities also, the tank type here is non-pressurized kind. We will also look at pressurized though. So with 8-degree supply and 15-degree return temperature is what it is designed for. And just for you to have a quick look, the dimensions are then calculated depending upon, see, once we have the load capacity, once we have the storage capacity, and we can decide on the number of tanks we want to make. Like in here there is one tank only, or there can be multiple tanks also. The tanks can be shaped, either they can be a rectangular tank also. Like in here it was a rectangular tank, it was an RCC tank, to be precise. And these tanks can also be MS. Sometimes they are also of MS, and they are cylindrical in construction also. So we'll try to understand this term as well, figure of merit. This is something which is applied. This is storage efficiency, which is applied for calculating the net volume of the thermal storage tank. And then there is also a calculation based on the peak flow across thermal storage, and the pipe size is also calculated, that what will be the inlet outlet connection size of the stratified thermal storage tank. Just to quickly understand the schematic, how the schematic works, how the flow works in a demand management system, in a thermal storage system where the objective is demand management. Uh, so there is a chiller with a primary pump, and this configuration is a primary constant, secondary variable, and this is how the uh, this is the stratified chill water tank here. And these are secondary pumps, and this is our building load. So this is the general schematic, and we will also try to understand these schematics for various modes of operation as well. Although I could although in here I will explain you that there are generally four modes of operation. uh, like one is chiller, uh, chiller only cooling. Now, when the chiller is only cooling and thermal storage is not required, these valves stay closed, and this one opens, and the flow, and whatever the load is, the corresponding to the load, the chill water is drawn down to the load, and whatever, if at all any excess chill water, excess flow is coming from the chiller, it is then bypassed here. So that is chiller only cooling. And there is also a scenario when chiller and thermal energy storage both are cooling. So with when the chiller is when the load is beyond the chiller capacity, the storage here will also come into play, and the secondary pumps will operate on the desired speed, and the excess water the excess water required shall be drawn from here, from the bottom. Discharge always happens from the bottom. Like in the density difference, we understand, like in stratification, uh, the cooler water will stay at the bottom and the warmer will stay at the top. So that is how natural stratification would happen. So the discharge always takes place from the bottom. So from here the chill water will be drawn, for a case when chiller and thermal storage both are cooling. There could also be a case where only thermal energy storage is cooling. In that case, the chiller will not operate, and nor the primary pumps. And in that case, the secondary pump is drawing the desired amount of flow for corresponding to the load, and the chill water is drawn from the thermal storage tank. So so from here, the warm water we see is returning back. After the load, the return water is warm and it is going back. So it'll go back to the primary pump. It'll come back to the thermal storage tank as well. So primary will suck as much it has to, depending upon its capacity. any surplus water that was drawn from here will come back to this. So this is so this warm water that is coming back. Uh, this is the mixing of this warm water should not happen inside the thermal storage tank. So for that only these top and bottom diffusers are used in a stratified tank. Now we should also understand how charging would take place in the same schematic. In in a charging mode, like charging is possible two ways. Uh, there can be a charging only mode in which chiller is only charging the thermal storage tank as not and not supplying to the load. Although it is also possible that chiller is supplying to the load as well for cooling, and any surplus capacity available with chillers, it can charge also, because charging too will happen from the bottom. From the chiller, see the water coming out and going back to the tank bottom, and the warm water is coming back from here and going to the primary pumps and again being sent into the chiller. So that's charging happening. For example, if our chiller is of 1,000 ton capacity and our load is currently 700 tons. So if it is delivering 1,000 tons, 700 tons could be sent here and balance 300 tons could be sent here for charging the thermal storage tank at the same time. So this is how we this is about the all modes of operation, all possible modes of operation in this kind of a schematic, wherein the idea is demand management. Just to show you the tank types generally, this is the RCC tank type. Uh, like they can also be RCC, in which only diffusers are installed, and there is also an insulation and internal waterproofing. Waterproofing and insulation is all internal in that case. And these tanks can also be of this kind. They can also be MS, and they are insulated, and the cladding is also done on them from the outside. These are cylindrical in construction. Okay, we will now understand the stratified thermal energy storage system design in a different application, uh, that is emergency chill water supply. This is mostly used in data centers. It's very popular these days, and the uh, the design of this has different considerations. Uh, so so what is the basic design data here? And here the see in so we could actually talk in terms of a data center application also, to be very specific, in which the purpose is to fill for the chiller and DG startup time during power outage. This essentially means that whenever there is power outage, and the cooling in data center is very crucial. Even for 5 minutes, no chill water supply could be fatal for a data center. So for that reason, to fill for that period when DG is also starting and chiller is also ramping up to its full capacity, for this time duration, a backup chill water supply is planned. This duration generally is in a range from 5 to 15 minutes of backup. And these are the tanks who we call a low volume systems. The previous one for demand management that we saw, they were high volume systems. They were large tanks, and these are going these now for this particular application can be termed as a low volume application. So let us say that the peak load of the data center is something like a 400 tons, and the supply water temperature is uh, 11 and return water is 15, and it's nearly 15 minutes backup that is being planned for. And so TRH is our thermal energy storage capacity. Like we convert 15 minutes into hours. 15 divided by 60. So when we calculate TRH using the tons and hours, that's what we get, 100 ton hours. It is also important that what is the pumping configuration in this scenario, whether it is primary constant, secondary variable, or whether it is primary variable flow, because for both the schematics are different. We also need to know whether what is the design pressure, what is going to be the design pressure of the thermal storage tank, what is going to be the system pressure, and what is going to be the working pressure, all these things. Because hydro test pressure is something that is done after the tank is manufactured, and it is generally done as per ASME standards, which is nearly 1.3 times the design pressure. So from constructional purposes, from integrity purposes, this data is also important. Location of tank is also sometimes that we should ask, where is it, where is it to be located, and so whether it can be terrace or it can be on the ground floor, it can be in a basement, it can be outside, it can be anywhere. This is something that we should ask, because this will actually affect the design pressure of the tank, whether the static is being added, because generally for a tank at the roof will have lesser design pressure, lesser working pressure. The design temperature is also important. That is from the insulation calculation perspective. So, what is the design temperature that is being considered? These calculations are done in a similar fashion, like we saw in the previous slide. Whether uh, whatever is the storage efficiency, depending upon the storage efficiency, this is worked out. The volume is worked out, and this is how these tanks are typically of this size, like something like a 3.5 meter dia. And the previous one that we saw was a large tank. It was nearly uh, 10 meter by 5 meter, and something like a 20 meter dia tank. So here you see the tank dia is 3.5 meters, and the total height is nearly 6 meters. So these are categorized to be the low volume systems relatively. Again, depending upon the charging and discharging flow rate, we arrive at the inlet outlet connection size. Uh, and so that's the sizing calculation essentially, as far as the sizing is concerned. We will now try to understand the system schematic with respect to primary constant, secondary variable, and also we will see how they are in terms of primary variable flow. So this is there are generally four modes of operation in these cases, and to start with, uh, I would actually explain that to you in the next slide. What is normal mode of operation? But this is initial charging mode, in which happens only once at the time of starting charging the thermal storage tanks for the first time at the site. So in here we have primary pumps, we have chillers, we have we have secondary pumps also, and we have thermal storage tanks. These are many, by the way. They are multiple tanks. They can be two, three, four as well. They can be a single one also. So in our initial charging mode, the chill water is coming from the chiller, and it is going here, and as I said earlier, that the charging happens from the bottom. So it happens from the bottom, and the warm water which is already present inside the tank is then coming into this header, and it is being sent back to the suction of primary pump for getting cooler again. That's your initial charging cycle, in which load does not come into play, as secondary pumps do not come into play. Now, actually, there is something about this schematic, uh, which is which in the data centers, which in the data center application, they have to be online type schematic, online, or some people also call it inline. Now, online inline is essentially it means that chiller while supplying, like this is our normal mode of operation, that the when the plant is running normally, when the chill water is coming out of the chiller, it is going inside the thermal storage tank first from the top, and then in the same chill water, these tanks are already charged. These tanks are now already charged, and the chill water is not directly coming to the load. It is going first inside the tank, then coming out of the tank, and then being sucked by the secondary pump and being sent to the load. So in here we see that a continuous replenishment of the tank water is happening, and this is inline system. This is done because in data centers the purpose is backup, and uh, backup an emergency backup, and an emergency is something that will happen randomly. It is not a regular thing to happen on hourly basis or every day, but it can happen any moment. So these tanks have to be ready and ever ready for discharging when required. So that is why online mode. Now let us switch to the next mode, that is the discharge mode. This is the emergency mode in which there is a power outage when the chillers are stopped. As you can see, the chillers are stopped and there is a need for thermal energy storage to discharge. So in that case, nothing but secondary pump is only which is drawing the chill water from here. You see from the bottom of the tank, it is drawing the chill water here, sending it to the load for the time duration it is designed for, and this warm water is then coming back to the top header and then going back to the thermal storage tank, the warm water. And right when the chillers have come back, they have ramped up to its full capacity, and the DG also came back. When the power is back, then comes into picture the recharging mode. The tanks discharged in the previous mode, and how the recharging mode would happen is that the chiller will supply to the load as well. You see, the secondary pump is drawing chill water from here, and you see this extra chiller has come into operation. See, in here, this chiller was off. This is our standby chiller, let's say, or but in a recharging mode, this extra chiller has also come into operation for a reason that these three chillers will be busy catering to the load. There will be required some surplus flow for the charging of the thermal storage tank. That surplus flow will pass from here. For example, if the load is 900 tons and the chiller are 1200 tons, so 900 ton will be sent here, and that 300 ton will be sent here for thermal storage to get charged simultaneously. So once they are charged, the system switches back to the normal mode. So these are the four major modes of operation. Now we will see that how what is the system schematic with primary variable flow pumping system. Like in here, you see there is only one pumping system, that is primary variable, the chiller, and we have thermal storage tanks also. So it's in a normal mode. Like initial charging is done in the same way, but let's start with the normal mode here, in which the chiller is coming, the chill water is coming from the chiller. It is going back to the the tank top, uh, the tank top had, connection, and the discharge is then is happening from the bottom, and it is going to the load. Then there is a bypass here. This will be used in the other mode. See, from here it is going to the load, and from the load it is going back to the suction of the primary pump. That's our primary variable schematic. Now, in discharge mode, this is the emergency mode in which chillers are not in operation. Nothing changes, everything remains the same way. It's just that the chillers are off. See, let us check this out. Let us check the path here. Uh, See, these pumps are operating, and these pumps are bringing the let us in fact start from here. That this chill water is being drawn here, being sent to the load. The water became hotter, warmer, and it is going back to the entrance of the primary pump. They travel across the chiller, they come here, and from this header they enter into the tank top. So there is no valve changing, also no valve position changing as such. So this is discharge mode. And right after this, in recharge mode, uh, the chill in the recharge mode, the chiller has to cool the thermal storage tank also. So has to cool the load also from here. See, it is going to the load, and see, initially this is closed because the first priority is to, of course, satisfy the load. Once the load is satisfied, this valve also. So no, in this case, this valve remains closed. See, uh, this is going to the load, and from here NV3 opens, and for the charging, the the chill water goes here to charge the thermal storage tank simultaneously. The warm water returns here, and it mixes with the return water here and goes back to the suction of the primary pump. So that's our recharging mode. Once this is done, we are back to the normal mode. This is how pressurized the steel cylindrical tanks look like. The application that we are talking about right now, these are the kind of tanks. Just to show you a pictorial view, this is these tanks are also hydro tested and painted, and then there's insulation and cladding happens on the site. To give you an idea about the CFD analysis, there is a CFD analysis also conducted for these tanks to ensure the parameters considered will help stratification happen or not, whether or not the tank and the diffuser is designed appropriately. So this is one CFD analysis, and you see the warm. This is happening while discharging. The warm water is coming back from the top. The chilled water is being discharged from the bottom, and you see in between here there is a layer. There is a mixing happening here. It's a controlled mixing. That is a zone which is called thermocline, which we will see in the slide coming. I have this picture here to show you that there are also uh, temperature sensors which are installed along the height of the thermal storage tank. Like there are six installed here, and the purpose of these are to uh, give you the status and the monitoring that what is the current status of the chill water inside the tank at what level. So so inlet outlet temperatures across thermal storage tank, and see, I would also want to highlight here that what are the important parameters with respect to which these systems are commissioned. And see, once the CFD analysis is done, so that of course becomes a reference point how the thermal storage system will perform. But inlet outlet temperature across thermal storage tank is recorded. Flow across the thermal storage tank is also recorded. Now, with inlet outlet temperatures and flow, we can figure out the tonnage. What is the tonnage that is being delivered? Now, there is interval frequency also recorded for all the readings that when it was recorded. Now, that is also summed up to calculate the duration, let us say 5 minutes, 10 minutes, whatever it was. or even hours for that matter, in a larger system. So that is also summed up and converted in terms of hours. And this tons and this hours, they are, when we multiply them, we get 10 hours. So the TRH for which we planned the system, that is something that we can practically calculate also. And this is something, this is an assessment which is done during commissioning. This is the testing, this is the performance testing which is done at the time of commissioning. These parameters are noted. Okay, the start time of discharge is also noted, that when did the discharge time start at the desired temperature, and the time until supply temperature was noted. For example, if I if I were to draw a 9-degree supply temperature, so I should be getting the 9 degree. Anything above 9 degree, no, my time has ended. So that is also something which is recorded to measure the time duration uh, of the backup which has been planned. Like I said earlier, the diffuser design is the heart of the system. So as far as the stratified tanks are concerned, if the diffuser is not correctly designed, the stratification will not happen, and there will be a lot of mixing that might take place, and the purpose will not be solved. So diffusers are designed. The radial diffusers is designed by inlet Froude number criteria as described in. So it is on the basis of design guide for cool thermal energy storage. So inlet Froude number is also an important criteria, and so is Reynolds number, on the basis of which these diffusers are designed to limit the turbulence inside the thermal storage tank. Now, I could show you a video here in which you see this, assume this red fluid to be the warm return water that is coming back inside the tank. The idea is to release the fluid inside the tank with a very low momentum, so that it loses its the momentum before reaching the wall of the tank. So that is something which is which leads to laminar flow across the tank, and that is what helps the stratification to happen. So that is the function of the diffuser essentially. We should also try to understand some terminologies from the design perspective, like a figure of merit. Figure of merit is essentially the storage efficiency. For example, this mixing that is going to happen. Okay, let us understand the second term before, thermocline. Thermocline is an imaginary layer in the tank with a temperature gradient that separates the cool and warm water. See, like in this curve, this is the depth of the tank. Let us see this as a tank. This is the depth of the tank, and this is the temperature axis. So at 15-degree temperature, uh, at the hotter. So it's the hotter water, the hot water is at the top, the cold water is at the bottom. So what is between these two? So between these two, that colorful thing, that colorful zone that we saw in the previous CFD, that is the mixing zone. That mixing zone is called the thermocline, that contains the temperature gradient between the warm and cold fluid. Now, since this thermocline has some thickness also, so let us say if my tank was a 5 meter height, and it was such that my thermocline thickness was nearly 1 meter. So my storage efficiency, so I'm not considering this thermocline as my usable chill water. So so in that case, my usable chill water becomes 80% of the total tank quantity, and that is my storage efficiency. So that storage efficiency is also termed as the figure of merit. The figure of merit is essentially uh, it indicates the loss of cooling capacity for the stored chilled water during discharging process. Like we may be able to discharge less out of what we charged in full. So that efficiency is a figure of merit. More terminologies: Froude number and Reynolds number. Uh, well, Froude number is generally the ratio of the inertia forces versus the buoyancy forces. The A low Froude number ensures that the buoyancy forces predominate over inertia forces and allow the chill water to be stratified. As per ASHRAE design guide for cool thermal storage, Froude number should be less than 1 for a good diffuser design. Now, Reynolds number is something, it is it is the ratio of the inertia forces versus viscous forces. It has more to do with the boundary layer of the thermal storage tank, but it's an important parameter for the diffuser design as well. Uh, so, so it is so as per ASHRAE design guide for cool thermal storage, Reynolds number should be in the range from 1,000 to 12,000. Depending upon uh, the mixing action affordable for achieving the desired stratification. So that was about the stratified thermal storage tank design. We will now start the ice thermal energy storage system design. To understand ice thermal storage system design, this is generally a demand management tool. So this is not essentially for data centers or for any other application. I mean, it is used the same way. It is used there is only one way it is used. So to understand the thermal energy storage system design, the ice thermal storage system design, let us first know what all are the components, important components of ice thermal storage system that together constitute to form a ice thermal storage system. So these are the major important things, important components. Thermal storage tank is something of great, of course, and then there is something called brine chiller, which is also used. It's a normal chiller only, but since the fluid that is used is monoethylene glycol, it's a fluid that is used. Like I said previously, you got to have a fluid which can actually flow and not freeze uh, at very low temperatures, as low as -10, -12 degrees centigrade. So you got to have a fluid like that. There are also pumps which are required. There are brine pumps required, and there are PHE pumps also required. And there is also thermal. There are also the pumps are required for thermal energy storage tank also, and also there is plate heat exchanger that is required. Uh, so these are the major five components of ice thermal storage system. See how all these components come together to make an ice thermal storage system. We can understand it by this schematic diagram, and this will also give us some idea about the system operation. We will also cover the system operation in with this very schematic. See, we have our thermal storage tank here, we have our brine chiller here, and we have our PHE here, and these are pumps, and these are pipes, and inside the pipes, inside the system is our monoethylene glycol solution, or either monoethylene or propylene, depending upon the application. Sometimes in some food applications, propylene glycol is also used, but generally for comfort cooling applications, monoethylene glycol is what is very popular. So this is how our so this is the schematic here. Now two things are supposed to happen. One, ice has to form, so charging has to happen. The second is ice has to impart cooling, and that's why discharging has to happen. So we need to understand how these modes of operation work. So we will look at two modes just now. Where I could see on the top. Uh, okay, so this is discharging cycle in which ice is melting. Now let us assume that we have ice inside. We have formed the ice inside the thermal storage tank. So okay, we also should know that on this side, like we have a PHE here. Why do we have a PHE? Because there is because on this side there is water flowing, and on this side of the circuit is our brine circuit. This is our brine circuit, and in a discharge cycle, see this pump is operating. Let us start from here. In fact, at 10 degrees centigrade, the brine solution is traveling here, and it is being drawn to the thermal storage tank. And across the thermal storage tank, it cools, the brine cools down to 5 degrees centigrade. And at 5 degrees centigrade, it comes to the PHE. Now, 5 degrees centigrade, it enters, 10 degrees centigrade, it comes out. And here the temperature is shown on the water side. Let's say they are 7 degrees centigrade and 12 degrees centigrade. So here you see the counterflow happening. From here, the brine is flowing, and from here, from bottom to top, the chill water is flowing. So 12 degrees centigrade chill water is entering, and 7 degrees centigrade chill water is coming out. That's how the cooling is happening on the load side. So here it is load side. So that's our ice melting cycle. That is discharging cycle. Now we'll see how ice is formed. See, for ice to form, uh, the chiller has to supply. I mean, chiller has to be able to supply. So we will also look at the chiller selection later on, in which you'll get to see that these chillers are actually a dual mode chiller. Like this chiller can also operate on the cooling temperatures 5 degree and 10 degree, like we saw in the previous slide, and also it can deliver minus 5 degrees centigrade of brine when it is like it is working on a 5 degree delta T. So how it is happening? Let us start from here. That minus 5 degrees centigrade brine solution is being pumped into the thermal storage tank to form ice inside the tank. And after gaining heat from the water and forming some ice, the warmer 0 degree centigrade brine solution comes out and goes back to the chiller with the help of this pump, this prime pump operating. So this is the charging cycle. See, that's a dual mode chiller. In this case, the PHE is not in operation. This is isolated with the help of a valve. Important design considerations that there we just saw the schematic and understood how it operates in general, and this is the design that how so for designing we need the design day load profile. We need the supply and return temperatures on the load side, like we saw previously, or 7 12. So we also need to know the building type, the application, from the space perspective, or where do they want to place them. Uh, So we also need to understand the purpose, whether it is load sharing or a tariff based operation. This is also something which is imperative. This will govern the hours of operation that we will see later. So we also need to know what are the hours of operation, whether it's a 24-hour operational building, or it's a uh, only it is only a partial, like 8 to 10 or something like that, 2 hours of operation, 9 hours of operation. Based on that, we need to arrive at the operational strategy. That what is going to be the operational strategy? Like there are generally three operational strategies. Like in here, these are 24 hours, and this green thing here, these green bars here show that thermal storage was used. And at the night time, here these blue bars are for chillers. So chillers stored the thermal energy at night time, and during the day operational hours, the entire time thermal energy storage was used. This is called full storage, full storage operation strategy. Now there is partial storage operation strategy. This is also possible. Like partly the load, these red bars, the load is being taken care by uh, the chiller, and this load up here, this extra load is being taken care by thermal storage, and the are chillers were busy charging the thermal storage tank at the night time. These are the night hours. There is also a scenario possible, something like a window storage. In window storage is essentially a combination of partial storage and full storage. You see, from here to here, it's a partial storage. Chiller is also operating, and in here is a full storage. And this is generally done in hours uh, where there's a power cut. Let's say where there is a power cut, and it is planned that for these five hours I'm going to have a power cut at my site, and I better not use chillers. I might want to use thermal storage only to save on my DG cost. Or there could also be a case that for these 5 hours, my tariff was very high. So I prefer not to use chillers during these hours, and I prefer using storage instead. So this is also possible, window storage. Based on that, we develop, our load distribution profile. Now, how do we distribute the load? Load distribution without base load. See, we will see why this base load comes into picture. Like it is for this kind of a load profile where the hours of operation is only during the day from here to here. At night, there is no load. For such cases, your brine chiller is operating, it is satisfying the load, and whatever extra load is there during the daytime is being taken care by thermal storage, like this of you. And here, your brine chiller is charging the thermal storage tank. So this is how it would be when there is no base load. No, when there will be a base load, how will it look like? Now, this is the kind of profile wherein you do have some load at the night time as well. So at the night time, uh, you see, and then there is a load that increases during the day. So this is the kind of load profile. So what you do is that you have a base load chiller. See, this system is going to be a brine system from here to here. However, in the load profile, in the next load profile, we will see that why is it required. Because here, you need to have a base load to be able to separate your to be able to make a profile like this, to be able to make a profile like this. And because if you separate your base load here already taken care by a water chiller, so you have only this much of load to be taken care, and that is where you can implement your brine circuit. See, please pardon me for this blur schematic, but what I wanted to show you here with just this one single slide is how is our total system schematic when we have a base load chiller as well. So let us say these are our base load chillers, and this is our load where this is our water circuit, chill water circuit, and this is our PHE, and this is our brine circuit. These are our brine chiller. This is our thermal storage tank. This is our pump that is taking the water into the PHE. So this is our brine side. This is our water side. So the only purpose to have PHE is to act, for it to be able to act like a third chiller in here. So this is our base load. This is what the difference is in the schematic with and without base load. So this is a load profile uh, that we have assumed, let's say, to understand the system design. And in this load profile, we have hourly load, and we also have uh, so we have a chiller operation, and this is our heat load, and we have assumed for a chiller to be of a size 450 tons. That's a 450-ton capacity. See, to arrive at the thermal storage capacity, trade-off between charge and discharge TRH is achieved. I have written this statement later, but I would like you to focus on this first. That chiller charging capacity is assumed to be 70% of the cooling capacity. Now, if my chiller capacity is 450 tons, so I assume that there will be some duration. Duration why? Because first I'm making my chiller run on in a cooling mode. I'm making my chiller run at 5 degrees centigrade. That is for cooling, and then when I'm charging it, then I'm making it run at minus 5 degrees centigrade. So I am making my chiller go down further in terms of supply temperature. So my chiller will be able to deliver lesser tonnage. So this is the deration that happens on account of charging when compared to cooling capacity. So 70% is what I have assumed. 70% duration is what I have assumed. Uh, so now the trade-off is achieved between the charging capacity. This is our discharging pattern, and this is our charging. We need to make sure that this this figure, this charging tonnage, is equal to the discharging tonnage, because we cannot store more or charge less. We need to have enough charging hours as well, and this is the reason why we need to have that base load chiller in place to get these charging hours. Because in chilled water, I could do my chiller could charge and cool simultaneously. But in ice thermal storage, my chiller's charging temperature is different and cooling temperature is different. So I really need to have some charging hours that are empty, that are available for chiller to charge the thermal storage tank at night. That's the reason for selecting a base load chiller in such cases here. So 3150 is like a TES capacity. When we sum this up, when we sum this discharge pattern, this is our thermal energy storage capacity. This is what it works out to be. Now, once we have thermal storage capacity, once we have the discharge pattern, see, before starting anything else, there is a guideline. There is a ARIT guideline for cool thermal energy storage, according to which very high load discharge over a short period of time or a relatively low discharge temperatures may reduce the usable capacity. When we are talking ice, see, if it was water, I could discharge all of it in whatever time I wanted. But if it is ice, Let us suppose that I want to drink a glass of water, and there is some cooling I want that glass of water to be cooled to an extent, to a certain extent. So if I have only one cube of ice, I'll put that ice cube in that glass of water, and if I want to drink early if I want to drink early, I might not be able to avail 100% cooling of it. Let's say I have a very less time, and that ice cube could melt only 20%, so I could not get my cooling 100%. So if in a lesser time I want to extract that 100% cooling, then I might as well put five such ice cubes in that glass, that each one of them melts by 20%, and I get my 100% cooling. That is one option. The other option is that I might wait. Then I might wait a little longer for that entire ice cube to melt and get my cooling. So here I'm trying to explain an analogy between between waiting more time and between more number of ice cubes. More number of ice cubes means uh, a high load discharge, and waiting more time is low discharge temperatures. Is low discharge temperatures. I'm giving more time. So my discharge, my ice melting is going to be temperature dependent and flow dependent. So as a thermal storage tank designer, as an ice storage tank designer, I should start thinking about these things. Looking at the discharge pattern, like my discharge pattern is here is pretty healthy. It's a long hours of discharge. Had it been only a 2 hours of discharge, let's say only a 1 hour of discharge, then I might have had a lot of unused ice. So there is a term introduced here called usable capacity. You see, usable capacity. That what is going to be the usable capacity in a given scenario at a given inlet outlet temperature at a given flow rate. So this is how on this basis the thermal storage tank selection is done, and uh, these these parameters are selected using the software which are built on the performance patterns of specific thermal storage types. These are different for different ice thermal storage tank manufacturers. Manufacturers, I would say technologies. For different technologies, they are different. To show you a glimpse of some software selection, like uh, like this is a selection for an ice spray system, in which first the application is entered, that what is the building type and what is the cooling load, and whether the unit can also be selected, it is kilowatt or tonnage. Like this is how the software is. This is and you see the load profile is entered. The entire load profile is entered here. A 24-hour load profile. There is also a calculation of the peak capacity here. It has been taken. It has been picked. You could also enter, or although it fixed by default, but you could also enter your base load chiller capacity, that out of which out of the total load, this much you want to have, this much should be the base load chiller capacity. And you see there is also, some people also come up with the software that in which they can also enter the tariff rates also, and this also does their energy analysis and cost benefit analysis also for them. So so on the basis of data you entered, it develops a cooling load profile, and this is also important data that needs to be entered, like the chiller data. You need to enter the chiller data on the load side as well. And see, you enter this on the load side, the supply and return water temperature. You also enter the data that goes into the phe, leaving brine temperature from chiller, that is the chiller outlet temperature while charging. while charging, and there is also the energy efficiency ratio calculation, which is done automatically, and then there is a pump head also that you can change, although it picks automatically, but it can be altered. Geographic data, usable usage data. I mean, number of days. You can also enter the number of days you want to use it for. If you think your building works 250 days or 300 days a year, you can enter that. So this is a kind of an output that is generated. This is a graph. Okay, it's a 24-hour load profile that is segregated between three components. That one is your base load chiller, and then there is your brine chiller, and then there is thermal energy storage, cooling, and these are your charging hours. So all this is generated. This is additional output, and this is like storage capacity, total thermal storage capacity. This also it works it out, and this also this is for IC is ice cubes essentially, ice capsules rather, ice capsules, and or what should be the total volume? Based on total volume, you can calculate the tank volume also, and what is the maximum discharge capacity. Uh, so this is our peak load on thermal storage. So we can plan our pump flow rate also, although it is done automatically in the software itself, but we can manually do it also. Chillers, the chiller cooling temperature, uh, as well as the charging temperature, that is also generated. The chiller cooling capacity and charging capacity, that is also generated. So the heat exchanger data, the PHE data is also generated. That what is going to be the in and out. That all this we will see separately one on one, for individual items as well. And there is some electricity, annual cost and consumption. All these things are also worked out. This also, this is in addition to the software output. I mean, this is also a part of it. It also generates a schematic depending upon your requirement, and it also suggests the uh, the, the chiller capacity reduced by how many percentages, the electrical capacity reduced by how many. So all this analysis gives you. So that's the kind of software output that is this kind of software that is available with the ice thermal storage manufacturers these days. So, so once we have designed the thermal storage system, we actually need to put all these, uh, we need to arrive at their selection parameters also, so that all these separate parts can be given to their experts. For example, once I have designed the thermal storage system and I know its supply and return performances, supply, the inlet outlet temperature, so which of course we know that will be during the cooling. See, I want to highlight something here. Like in this slide, we are defining the chiller selection parameters so that we can give it to our chiller manufacturer and tell him that this is what we need. And this is basically the chiller specifications. Your chiller should be able to deliver 450 tons as a nominal capacity, and it should be able to deliver this at these temperatures. Brine outlet temperature is 5 degrees centigrade and inlet temperature at 10 degrees centigrade. At these temperatures, I should get these. Plus, I should also specify them that at in charging mode, my chiller capacity should be this much. This is how much I need, 315 tons. At these temperatures, at these charging temperatures, 0 and -5, I should also specify to him what is the fluid type that I'm using. Let's say 30% monoethylene glycol solution is in water is what I'm using. So that also he needs to know to select his chiller. He needs all these parameters, chiller selection parameters. Okay, we need to be aware of something here, that Nominal capacity is the derated chiller capacity on account of low temperature and high density fluid. So it might be possible that uh, that the chiller here was actually a 550 tons rated capacity, and the temperatures and the temperatures you demanded and the the solution that you are using to run this brine chiller uh, is making it derate down to 450. So that is also possible. So so these chillers are, this is the derated capacity with these not the rated capacity. But anyway, the chiller guy will take care of it uh, when you give these selection parameters. Now we also need to define the PHE selection parameters, because a PHE also needs to be, the PHE guy also needs to know what all parameters will be required. So primary side, the PLC will only come into picture when there is cooling happening. So 5 degrees centigrade brine in and 10 degrees centigrade brine out, which is our primary side, the cold side, and that is the brine side. The secondary side is our water side on the other side, which is hotter. So the water in is 12 degrees centigrade, water out is 7 degrees centigrade, and we will also mention the corresponding flows on both the sides, because the load on the PHE will be the load on the brine circuit. So according to the load, the corresponding flow can be given on both the sides. Pump selection parameters, these also we need to give to the pump guy, that this is the kind of pump that you have to come up with. Uh, we need to specify the fluid kind. We need to tell him that this is the fluid that we are using, and this is going to be the specific gravity, so that he can apply the density correction while selecting his chiller. Of course, the load will be uh, the head will matter, so that head calculation can be done. It is done by the software as well, but if at all it is required to be done in the real time, so that is also possible. So monoethylene glycol concentration as water is nearly 25 to 30% is what is generally practiced in ice thermal storage systems for comfort cooling. So that nearly completes our ice thermal storage design. Also, we have selected the base load chiller. Pardon me, it should be the brine chiller here. We have selected the base load chiller. We have selected our brine chiller. We have done the thermal storage tank selection also. We have done our PHE selection also. We have done our brine chiller pumps also. And there are TS pumps also that we have selected for the corresponding load it is bearing. And we have selected our PHE pumps also for the water side. That would anyway be like a primary pump for chillers, for the base load chiller. And then there will be piping and desired instrumentation, which will together constitute to become ice thermal storage system. I would now like to quickly summarize of what all we have gone through in this presentation, and types of so we generally understood the types of thermal storage system. Two types: water based and ice based. We talked about stratified tanks, we talked about buffer tanks, and we talked about ice based systems, ice on coil technology, submerged nodules as category. And if I were to talk, I mean, that's just an opinion. But in stratified thermal storage tank, the diffuser, yes, that is very important. The diffuser is the heart of the system. Like I'm again saying, that's the key. It is, its correct design is crucial for optimum performance. And radial diffusers are best known for their sturdy structure and minimum pressure drop. And as far as ice thermal storage tank is concerned, uh, it is much about the correct design and implementation of the system as a whole. And ice spray technology is known for its least pressure drop because that is something that is an open circuit, and the spray mechanism is because of the spray mechanism it's an open circuit, the pressure drop is very less, and it is known for its best usable capacity also, very high usable capacity. It can go very close to the sensible. So these are some general findings as far as the study is concerned, and that concludes what I had to say on my part. And I invite you to uh, the Q&A session, and I can take questions. I have along with me with our Mr. Lalit Malhotra also. So for the Q&A session, I don't know if I have to go through chats, get these questions. And I believe that people one by one can ask these questions as well. I mean, I don't know if that's appropriate because
Uh, Akash, there are some questions in the Q&A.
okay, okay,
We can answer those questions.
okay.
So should we take one by one, sir? And
Yes, that will be okay. Yes, and in fact, whosoever asks can can voice it out also. Now that we are in Q&A session, although I'm looking. Mr. Ganesh asked how to do analysis of TES using an ANSYS. Okay. Uh,
Hello.
well,
hello.
hello. Yes.
You can show that slide
Yeah. Which one?
where you are showing the discharge mode cycle, video cycle of discharge mode.
Discharge mode. Ice. The ice thermal storage.
No. Our
Okay. Okay. The stratified chill water. You mean?
yes.
Okay. In which mode? Uh,
First of
but
all, also try to ask who's asking and his details or his, so that we can also answer them through mail also.
yeah. I mean, in fact, the question I just read, I'm not able to relate. Analysis of TES. If I may ask Mr. Ganesh, what kind of analysis he is looking for? Is it a cost analysis, cost benefit analysis, or is it a energy analysis or
Performance analysis.
performance analysis? See, as far as the performance is
Show that
concerned,
video. Show that video
which
where tank is discharging. The video
yeah,
animation video.
uh, long. Yeah, this one.
Yes.
Okay, okay, that's a CFD analysis, and the
It
performance.
validates the design.
Correct. Yeah, it validates the design, and see, CFD first thing validates the design that all the your tank sizing and your diffuser sizing and temperature and flow and velocity parameters are all in place to get a suitable flow pattern inside the thermal storage tank. So once every analysis is done, secondly, whether or not you get the uh,
desired time.
the desired backup time is something that also you can check by start time and the time until the temperature was noted. And plus, you can, of course, get the readings of the total TRH that you stored. That is the unit of thermal energy stored. So that's thermal energy you stored. So, so that also has a certain way of measuring it. Inlet outlet temperatures, flow, and time. So that gives you TRH. If I understood the meaning of the performance analysis correctly. Uh, okay. Why high velocity nozzle is used in octagonal tank diffusers? Does it not create turbulence? Uh, Actually, this is a little controversial too. I mean, for this reason, only some people do not prefer octagonal diffusers also, uh, because these nozzles are because nozzles are anyways high velocity. Since it's a network of pipe and octagonal diffusers, so it is anticipated, it is expected that there will be uh, release of water from the nozzles at different points. I could show that to you in my. So it is controversial, and that is why it is not a very highly practiced. It is just a type that I told you. It is not something that is highly preferred until the tank is very large. No, and V3 should be provided just after the chiller to avoid backflow and avoid for the same reason. So Prashant DK. Well, we can certainly look into it. Uh, see schematics. See these schematics shown here was generally to show the path of the flow in the circuit. I mean, if at all, I don't know if I should go into the schematic and check for the MV3 correction right now. It may you may be right also, sir. You're saying, please correct me if I'm wrong, but you may be right also. Uh, so, so I think this can be sorted. Uh, but as far as the system operation is concerned, I believe we understood. Is this RCC tank connected in a closed loop system? Is it holding system pressure? Sir, RCC tank is generally an open tank, and it's a non-pressurized tank. So it is not in a it can't be called as a closed loop system. Just things like overflow are taken care. There is an overflow connection also, but it is generally a non-pressurized tank.
Sir, I think should I read one by one question? It will be easier to take you, I think.
Yes, absolutely. That would be great. Yes.
Yeah. So next question, should we take it further? I mean, I hope you answered previous question.
Yeah, yeah.
Yeah. How important is thermocline is defining the effectiveness of TES, and how much thick is thermocline in a normal TES? Can you specify a few reasons for no thermocline in TES and how to correct it?
Absolutely. See, thermocline is something which will happen. It is. Okay, I want to show you that slide. Or maybe let's just stop. I wanted to go down that slide in which see, you see here that in here this colorful thing is a thermocline, and whether or not thermocline is see, thermocline can be thicker also, it can be thicker also. It is actually volume versus flow ratio dependent. For example, in a if in a large tank I am okay, let's start with a small tank. If in a small tank I am entering water with a very high flow, high turbulence is likely to happen. Now, with that high turbulence, the thermocline thickness could be more. It is likely to be more. However, for the same flow, with the same flow, if I enter water in a very large tank, in a very large volume tank, the relative effect of the turbulence could be very less. So, thermocline in that case could be very low. Or rather, let us talk in terms of percentages. Like in a small tank, your thermocline could be covering a 20% of the height or 15% of the height sometimes. But in a very large tank, your thermocline could be covering only 5% of the body. So it is largely temperature, it is largely volume versus flow dependent. And yes, when there are two different temperatures and flow happening within the same tank, thermocline will occur. It cannot be completely eliminated unless the flow is negligible, so negligible that even the diffusers are not required, something like that. But that's nearly impossible. It doesn't happen. So that would be my answer.
What study of load profile, what data required early, daily, monthly, and
Ideally, okay. Ideally, the peak month data is required. Let's say something like a May, June, July. These data, whichever was the hottest month, for that data can be considered. And often these load profiles are diversified also. That is what is considered for load profile. That would be my answer.
this is from the commercial side. Next question is we cannot take it in this forum. Might be you can connect with later on, sir. I mean,
Sure.
what is the tentative cost TES CHU type tank based on mixed combinations of chiller?
It's all so variable, so vast, and it is project
Yeah, right.
specific, and it's different.
Yes,
It
definitely.
cannot be, yeah.
I think it will take
Lot of
time as
inputs.
well to
It
calculate
will
all
take
the
lot of
systems.
inputs to arrive at a
Yeah.
specific
So definitely we will
time.
answer it, sir. But later on it will be answered by speaker, sir. Should we take next one, sir? Next question.
Absolutely, yes.
Yeah. How we can increase delta T to increase better performance, high energy saving in existing installed absorption chiller connected piping loop.
See, increasing the delta T is definitely of great help as far as the energy efficiency is concerned. That will also reduce your
Tank
flow,
volume.
and yes, that will also reduce your pump flow also, and that will also reduce your storage volume also when it comes to stratified thermal storage tank. So it will reduce your volume in the proportion that you have brought down your in the proportion in which you have brought up in which you have raised your delta T. What I mean. So it is of great importance. It's a wonderful thing. It is a way of optimizing your thermal storage tank size. Yeah, that is my answer.
Okay. So moving to the next one. Thanks for your very good and simple presentation, sir.
Thank
Sayed,
you.
Mr. Sayed is complimenting you.
Mhm.
How important is thermocline is defining the effectiveness of TES, and how much thick is thermocline in a normal TES?
I think I answered this one
Yeah,
previously.
it was taken.
Yes, yes, I answered this
Okay,
one.
so why it is coming again? Anyway, uh, moving to the Q&A section, that is from the chat one. We have started chat one.
Yeah.
Uh, Please look into the question that we have answered already. So let me know, sir. We'll skip that question. What is the average pressure drop and stratified tanks and baffle type tank?
See, as far as the difference in pressure drop is concerned, there is hardly any difference. It's just that actually it depends on the diffuser type also. Like in a buffer tank, there is hardly anything. There is nothing, and except for the baffle plates, and uh,
There will
and
be more pressure drop because the flow is moving in multiple directions within the tank. So there will be much more pressure drop than the our stratified tank with the radial test diffusers.
yeah, and on the other hand, if it was to be an octagonal diffuser, which is made of a network of pipes, so that is something is that has a very high pressure drop. However, radial diffuser happens to be the category with least pressure drop because the flow pattern is very simple. It just goes inside the tank and releases the water radially. So the pressure drop is very less, as low as 2 to 3 psi, nearly nothing.
Chiller and heat pump and normal air conditioning. What is the differences?
Relevant.
I would say this is irrelevant to the session. Uh, yeah, I mean,
That
So
is a
please,
different topic. It's
yeah,
it's a different topic. Yes.
uh, please explain how secondary pump will deliver excess flow during chiller plus TES tank, both active mode, for creating high loads in the building.
When the load is higher, I will take you to back to this slide. When the load is higher, let us say our chiller capacity is let us say our chiller capacity is 700 tons and our load is 1000 tons and our thermal storage tank is capable of handling 300 tons at a time. So when the when the load is 1000 tons, the secondary pump is operating at its full speed. It is ready to draw 100% flow. But this is give thermal storage. This chiller is delivering only 700 tons. So balance 300 tons will be drawn from here. It will be drawn from here. See, this is what is it? You see no secondary no pump here. There is no pump. See, there is like unlike ice case. Like in ice, there was a separate TES pump, thermal energy storage pump. For here, there is no separate pump. Here, with pressure, with suction pressure in this line, the water is drawn, and whatever the load is, it is entirely taken care. Yeah, so that's my answer.
What is the buffer volume required in a tank as against the calculated volume?
Buffer volume required calculated against the again calculated volume. I don't know. This question is actually not clear, but let us say if somebody is asking about the difference between the buffer tank volume calculation and the stratified tank volume calculation, I assume the question was this. So My answer would be that in buffer tank, the mixing is not accounted for. That thermocline that we talked about in stratified, which we must take into account, because that mixing for sure will happen. If my tank is, if my buffer tank is sized exactly for 100% capacity, by 100% I means exactly flow multiplied by time. That's my volume. If it is designed exactly for that, then when the return water comes back during discharge, some mixing will definitely occur, and
Percent mixing will happen.
because of diffuser not being present there, actually the turbulent mixing will happen there, and it might spoil 70-80% of the water already, because you want to draw 7 degrees centigrade water, 9 degrees centigrade water, and but your 15-degree return came and affected all your 7-degree water and turned it into something like a 10, 11 already. So what is it that you are left with? So this is something which is not taken into account in buffer tank. However, stratified tank, thermocline is separately taken into account, and the arrangement of diffuser is there. If you ask me, the right way to store chilled water would be stratified thermal storage tank. That is technically the most correct method of storing chilled water. That's my answer. That's my answer.
Next question is one. Is there a limitation on diameter to height ratio on of the tank?
Yes.
Yeah.
Yeah.
Yes. I mean, the height cannot be very less. There has to be sufficient height for thermal stratification to happen. Although it is seen that um, the height and the diameter may be same at times, but if the diameter is very low or something like a half, I mean, if the height is very low or something like a half of the diameter, a tank like that may not be very. See, if you go on to expand your diameter and reduce your height, what are you doing to your thermocline zone? See, the thermocline height is going to be the same. If you want to increase the area, you are letting more water inside the tank to be unused, because it stays in the zone of thermocline. So it is always better to have a trade-off between in the height and the dia, and uh, and and yeah, because you cannot squeeze down the diameter also and have a very tall tank. That also can be challenging. That also has limitations, because you have flow constraints, because per tank flow is also something that will limit you from decreasing your diameter. So with experience, all that will come. Uh, that what would be the most appropriate height for a specific
Should
tank.
we take the next question, sir?
Yes, absolutely.
Yeah. In data center for emergency backup, which is very useful in economical viable, TS tank or buffer tank?
I would say any day the TES tank, the stratified tank. If you talk economically viable, yes, both are viable. Viability is not a question, but a much better technology, and the right technology, I would say, go with is a stratified thermal storage tank. Buffer tank, I would say it is just a provision. It is only a provision for namesake that yes, we do have thermal storage. We do have something called chill water storage tank. Thus, it is specified in terms of KL, that this is the kiloliter I need. It is never specified in terms of TRH, that this is the thermal storage capacity we need.
or the time also.
Yeah, even the time is not specified. They don't say I need 5 minutes, 10 minutes, 15 minutes. No, it's just 1 kL.
What is diffusers? What is diffuser and its role in the system?
See, diffuser, like I already said, it's the heart of the system. Diffuser is the one that is going to diffuse the water that is coming inside the tank. And a rightly designed diffuser will make sure that the water inside the tank is released and sucked in a manner that turbulence occurring inside the tank is minimum and the thermocline thickness is minimum and the storage efficiency is maximum for maximum possible usable chill water volume. So diffuser design is very, very critical for stratification to happen. Just anything cannot be a diffuser. It has to be rightly designed, rightly constructed.
How much energy saving we can have using TES?
See, it is all application specific. I would say it's project to project. It is generally dependent upon your load profile. For example, if you have a very flat load profile, a very flat load profile throughout 24 hours, then it may not be very beneficial for you also. But if you have a reasonable variation in the day hours or even in the 24 hours, like you have a more load during the daytime and less load during the night time, and also you have differential tariffs. Let's say you have a lower tariff at the night time and and higher tariff during the daytime. So that advantage can also be taken. And despite that, I mean, even if it's not there, even if differential tariff is not there, there are also chances that mm, like if you store thermal energy at night time using your chiller and use the cooling during the daytime because it is anyway more efficient to run the chiller at night time than the daytime. At night time, chillers will have to do less work because it will be already cooler out there. So I hope that answers the question.
What maximum backup time is recommended ice-based system for ice-based system? Can we use TES in is existing chiller also? I think in existing chiller also. Okay.
Could you repeat that question once again?
What maximum backup time is recommended for ice-based system? Can we use TES for existing chiller also?
Oh, chiller. Yes, yes. For existing system, the chiller can be for existing chiller plant. It can be used. There are a lot of retrofit jobs that are also done, and it is it is easiest. In fact, very viable with chill water storage tank because already a fluid is there. A chill water fluid is there, and although capacity expansion is possible from both ice as well as thermal storage tank possible, but if it is only a thermal storage tank that is to be integrated with an existing chiller plant, uh, I would say chill water storage is most somewhat better suitable given the space is available. Uh, Space is available. If space is a challenge, ice is something that can be looked at.
Is there
Uh,
any special criteria? Well, have you finished the answer, sir?
Yeah, yeah, nearly. Yes. Yeah, yeah, that's okay. That is all. Yeah. Tell
Yeah.
me.
Uh, Moving to the next question, is there any special criteria while selecting the cooling tower for brine type of chiller application?
Uh, could you repeat that question once again? Is there any
Is there
specific?
any special criteria while selecting the cooling tower for brine type of chiller application?
Okay, okay, all right. See, no, I mean, it is there might be there might be you know specific there might be stringent requirements for cooling tower selection in that case, in that sense, but but even that totally depends on the chiller selection guy, the chiller guy, how he plans his chiller, what his condenser is like. So depending upon what his condenser is demanding, cooling tower will be selected. So I think that is a very far off picture, and I would also say that is not of much relevance. I would keep my limits down to the brine chiller at most. So that's my answer.
Yeah, I think this question is the extended version of the last one. Is there any special criteria while selecting chiller pump primary and secondary due to low temperature application -5 degrees Celsius? Name of the software used for thermal storage system data analysis selection of. Sorry, sir, we cannot take any name in company name in this forum,
Exactly,
like software or
exactly,
anything due to some protocol.
exactly.
You might
And
connect the speaker later on
yeah,
for
but
this.
the pump, but he asked about whether there is a criteria for pump selection. That
Yeah,
can be
yeah,
answered.
yeah, yeah,
And
right.
see, it's nothing. It's just the fluid type. The way you do, you specify flow, you specify head, everything. You just need to specify the fluid as well. So the density correction factor is applied while selecting the pump. That's all. That's all you need to do. That's the answer.
What type of maintenance required on time based, or what is the life of thermal storage system effective performance?
See, the life expectancy of thermal storage systems are generally, it's a range between 15 to 20, sometimes 25 years also. So these are very long-standing, in long-lasting tanks, and and maintenance as such is not required. I mean, it's actually manufacturer to manufacturer dependent. Some manufacturers need. If for a stratified thermal storage tank, if the water quality is maintained rightly, that is all the maintenance that is required. Because generally, for a good construction inside the tank, and the material and painting will be taken care. So there is no maintenance required as such. However, there is some maintenance required in ice thermal storage system. uh, like in ice thermal storage system, one really needs to every now and then, not every now and then, but a check every 3-4 months is done, whether the right concentration of monoethylene glycol is being maintained inside the water or not, into the circuit. And also the water quality. If the tank is of the type wherein it is filled with water, and if something like an ice on coil thing, in that case water quality needs to be maintained. However, if it is kind of an ice capsule, so the water is already inside, so that does not need to be maintained. So I would say it is manufacturer to manufacturer, and I would rather suggest you to talk to individual manufacturers to know the maintenance information about specific system types. That's my answer.
Yeah, the last question that I'm looking for, that is minimum tank height required for stratification.
See again,
Stratification.
yeah, stratification. See, it is again flow and volume dependent. I could have a tank as big as a 20-meter dia and 15-meter height, and I could also have a tank as big as 4-meter dia and a 7-meter height, and I could also have a tank as small as 2-meter dia and 4-meter height. It all depends on the flow, my flow per tank. my flow should not exceed. So I cannot have a very high flow going into a very small tank. So stratification has a lot to do with flow versus volume and diffuser design, of course. So I would say it's all case to case basis. There's no minimum volume. If you were to ask me a minimum volume, I could build a tank as small as 1 meter height, and I could still make the stratification possible. But that is practically very unviable. Yeah, that's my answer.
Yeah, and that is so finally done. And I believe it was wonderful session, sir. And we looked at more than 24 or 25 questions has been asked, and you have answered very well with patient. And thanks for all the attendees for patient hearing. Uh, uh, this shows that how the involvement, how the attendees were well involved, because more the question, more the involvement is directly professional. What we can say, and
Absolutely.
25 plus question is showing that it was the great involvement of all the attendees in this webinar. And of course, we count this webinar as a great success uh, in that in this parameter. So thanks for your time that we have spent with us, sir. And before going to the last section, that is vote of thanks that will be executed by President of Delhi Chapter of ISRE, Mr. KD Singh. I would request everybody who is non-member here, they can join us. Link has been already given in the chat box. Very easy to join. You will have to just click the link. There will be option for membership joining for 3 years and 10 years. You will find out the link. You can easily find out the link. When you click over there, you will have to just select Delhi Chapter of ISRE for joining Delhi Chapter of ISRE, and you can have to fill up all this stuff related to your qualification, your experience, and all this detail you have to fill up. Then it will redirect to the payment page, and immediately will receive the uh, confirmation so that you have now ISRE member after sending the payment. So this is the society, and membership is our strength. That is why we are asking more and more of joining of yours in this society. Will definitely boost up our morale to make this kind of program more and more. So this is the thing that I would like to say finally. And now I request President of Delhi Chapter of ISRE, Mr. KD Singh, to execute vote of thanks.
Good evening, everybody, and I think thank you for this wonderful session. My heartfelt thanks to both Lalit and Ekansh for this wonderful presentation that you've made. I think whoever has been on this program, this thermal energy storage systems have been made have very simply been explained, and all of us have gone back more knowledgeable from here. It's a wonderful topic, and I think one of the very relevant topics in the present times, where we are talking of the economy growing at the by 2030, India is projected to be a $10 trillion economy. So which means a heavy load on our infrastructure. So maybe if we are able to work on the thermal storage system effectively and are able to design systems, which can work on the thermal storage concept, probably our connected power load which is required for the same air conditioning capacity could be much lower for data centers and for many other applications. I think it seems like a very useful concept to follow. So thank you, Lalit Malhotra ji. Thank you, Ekansh ji, and thank you
So
to
much.
the entire DCI admin team, the all the attendees who've been here today. All that we can assure each one of you who are the members of Delhi chapter of ISRE, that our endeavor will be to bring you more and more interesting programs as we go along in the society year. We have some more interesting programs lined up for this month. We have two international speakers who will be on the DCI show on the 14th and the 16th, and we really look forward to your presence, your attendance, and to get you an international exposure on the latest carbon standards as we move towards our goal of carbon neutrality in the mid-century, by 2050, India is poised to be a carbon neutral country. So the latest international standards on the carbon emissions and also on thermal comfort. 14th is where we come up on the thermal comfort, and on 16th we come up with the new carbon standards worldwide. So we look forward, and then we have something coming up on radiant cooling by the end of this month, a workshop. Next month we have a workshop happening on chill beams, on design of chill beams. So we promise to bring in more and more interesting programs, more value to all our members. So we encourage you to be a part of the Delhi chapter of Fisher. You are our strength, and you can only motivate us. So thank you, Lalit Malhotra ji. Thank you,
Thank you, sir. Thank
Ekansh,
you so much, sir.
for
Thank
Wonderful.
you,
being,
KD
being
Singh
here
sir.
on, for being here on the show. I think we are really highly indebted to you for having shared your knowledge with us. I personally have enjoyed every minute of the presentation. So thank you, everybody. Thank you very much, and
Thank
thank
you once
you,
again.
Tapas ji,
Thank you very much, sir. Thanks for your involvement, sir.
for
Thanks for your
having
time.
organized a wonderful program today. Thank you very much, and the entire DCI team. Thank you very much.
Thank you, sir. So, with your permission, I'm going to close this session now,
Yes,
sir.
please. Thank you so much. Thank you.
Thank you.